So here we're going to check out 5.1 operations with functions. And here's the why. We often design things in a way that allow for multiple steps to be taken all at once. Operations with functions does this mathematically. Some examples of this are quite easy. If you think about hole punching a stack of papers, you have a couple different options on that. You could take each piece of paper and hole punch it individually. You would also have the option of stacking several of the pages together and hole punching them simultaneously. That would represent more so operations with functions, to where multiple things are happening at the same time by combining some of the steps. Some of the more interesting and complex versions of this will be a situation like this. A group of college students is planning to rent some single-seat kayaks, one kayak per person, during their spring break. The cost to rent the kayaks is $60 each, plus a one-time non-refundable security deposit of $50. The students decide to split the cost of the kayak rentals equally, and that the student who owns the car in which they drive will not have to pay for the kayak rentals. So what we're going to be able to do is ultimately create a function, right? And we'll see that its notation is different from things that we've seen in the past because of operations with functions. And that function will allow us to calculate two things at once. It will allow us to calculate how many individuals are paying, because the driver doesn't pay, so it's always different than the amount of people going. So it allows us to count how many people will be paying, and it will also help us determine how much each person has to pay depending on how many people are paying. So it'll be doing multiple things with one function. And that's some of the benefits of operations with functions, is that you can have multiple steps like that taking place all at once, and we will do that by combining functions. So when we see this down here, they've given us two different functions. They gave us f of x is equal to 2x plus 5, and g of x is equal to x minus 6. And then there's some different operations that they'd like us to do. Now, this notation right here may seem complicated to you because we've never seen it. And here it has f plus g of x, or f minus g, f multiplied by g, f divided by g, all the different single function operations there, addition, subtraction, multiplication, and division. But we will see after completing some of these that these concepts are quite simple to do this. Function notation has always worked as whatever you see replaced for your variable, it's telling you to substitute that value in. So as a review, if I gave us f of 2, what that would prompt us to do is to go everywhere that there's an x, replace it with the 2. Okay? Now, this notation here, f plus g of x, the x still works the same way. It would tell us what we are plugging in for x. On this particular example, we're not plugging in anything for x. We're going to leave it just as x. What the f plus g is telling us to do is, hey, before you go in and plug anything in, which in this example we're not substituting anything in for x. We're going to leave it as x. But it says before you do that step, add your f and g functions together. And what that would look like is, if f was highlighted in yellow, g was highlighted in green, we will add those two things up. So I will do 2x squared plus 5 plus, because that's the operation that they gave us, the x minus 6. And when I combine those, I'm looking for like terms. So 5 minus 6 is a set of like terms. The x doesn't have any other like terms, so he'll just stay by himself. So what this tells us is that f plus g of x is equal to 2x squared plus x minus 1. So that is those two functions put together. So now, if you were to substitute a number in, and I'm going to pick a number and have us try it so that you can see this happening, using the f plus g of x equation will be more time efficient because things are already put together. Say, for example, here, and I'll stick with this f of 2 situation up here that I picked previously. Say I wanted to find f of 2 and g of 2. Okay, g of 2 would end up equaling -4. F of 2, 2 squared is 4, 4 times 2 is 8, 8 plus 5 is 13. F of 2 is 13. I could manually add these up, the 13 and the -4, to get an answer of +9. So that was me calculating f of 2 and g of 2 separately and putting the 13 and the -4 or the -4 together. Now notice what happens if I use the f plus g of 2 function that we already prepared. When I plug in 2 here, we have 2 times 2 squared is 4 times 2 is 8. 8 plus 2 is 10 minus 1. You get the same answer of 9. So what function operation or operations on functions allows us to do is take a situation that I would have needed to do in 2 parts, to where I calculated f of 2 and g of 2 and then manually added them together. If I already have a function of f plus g, I can plug it in one time and get these same answers. So it's similar to if you had to hole punch two pieces of paper, you could hole punch them both separately, or you could stack them together first and then hole punch once. And that's what's going to be going on here in our operations with functions. All we're doing is putting two functions together with a certain operation, and then that way, if we needed to evaluate at different values, we would already have the function that has merged the two together. So say, for example, here, I needed to evaluate function f at a number, evaluate function g at that same number, and then subtract them from one another. And this could be used to maybe calculate profit. Because say you are a hot dog salesman. Everybody pretend that they're a hot dog salesman. And F can represent the profit that you make when you sell a hot dog, and G can represent the cost of having that hot dog in the first place. Because you had to buy the hot dog, you had to buy the bun and the different condiments. So if I made profit off of, say, 5 hot dogs, then I also had to pay the expenses of 5 hot dogs. So if I was going to need to be using this function over and over again, I could calculate, I could plug in a number into f, plug in a number into g, and subtract the two together. Or I could create, by using operations of functions, a function that has both of those concepts already incorporated. And I would do that by following a similar pattern from up above. I would take my function f, and I would subtract it. Now we need to be careful, because this right here says subtract g, which means I need to subtract all of g. So I'll end up having some distributing here. And now I can combine some like terms. So this would give me, for the final answer, for f minus g of x, where x can represent however many hot dogs I sold, as 2x squared minus x plus 11. And now, instead of having to plug in however many hot dogs I sold into my profit equation and into my expense equation, I could create f minus g of x and plug it in only to this function, it would tell me how much total money I made after selling those hot dogs and paying the expenses. That's operations of functions. We can do it with multiplication as well. Hopefully you're starting to catch on that it's really not too complicated. Here's what f was. Here's what g was. And when I'm multiplying them together, see, in this case, we are going to have to use the distributive property, but that's okay. We'll get a 2x cubed minus a 12x squared plus a 5x minus a 30. So f multiplied by g of x would equal our 2x cubed minus 12x squared plus 5x minus 30. And if we needed to, substitute in a number for f and a number for g and multiply them together, we could do them both separately and multiply the results, or I could plug in that number into just this function and it would do all of that work for me. I'm going to leave the division one for now. We'll cover that in class after we see this problem here, because it's going to get into a concept called domain restrictions. And domain restrictions will be a lot easier to understand with us looking at that kayak example first and then kind of breaking down the concept together.